We're back with our geometry review. This time we're doing page 2. I'm going to work this one a little bit differently than the first one. First of all, let's look at the answers. 20, 21, 22, 20, starting with 30. 30, 31, 32, 33, 34, and 35. I have false, false, false. 33 is true, 34 is true, and 35 is false. Okay, so let's talk about how some of these may be tricky. I think probably the trickiest one of the lot is 30. Talks about the angles of a triangle being supplementary. Well, we know the angles of a triangle add up to 180. That's not a problem. So if these three angles, we call them A, B, and C, you know that A plus B plus C has to be 180. So why is that not supplementary? Supplementary means, definition of supplementary. Supplementary means two angles that add up to 180. That add to 180. The definition does not talk about three angles. So by definition, number 30 is false. Okay, number 31 talks about secant segments to a circle from an external point. We should probably draw a picture. External point. These are supposed to be tangent segments are equal. So if these are tangent segments, they are equal. Secant segments would have to hit the circle in two spots. And you can easily imagine that you could have two secant segments that are different lengths. So that's a false statement. Number 32, corresponding angles of similar triangles have the same ratio as the corresponding sides. This is also false. Similar triangles simply mean the same shape. And in fact, one of the characteristics of all similar figures is the corresponding angles have to be exactly the same. So if we have a triangle and we have a similar triangle, the corresponding angles, let's say this one has to be the same as that, and then this one over here would have to be the same as this one over here, and the third one would have to be the same as the one up here. Okay? So yeah, corresponding angles have to be the same. The ratio of the sides could be anything. For example, if this were 3, this might be 5 or 6, and so the ratio of the sides would be 3 to 6, or if you did it the other way around, 6 to 3. And that is not the same as the ratio of the angles. The ratio of the angles has to be 1 to 1. Okay, 33 is an interesting question. It's a true statement. It is a syllogism. Now, in fact, it happens to be not true biologically, but if all sharks are fish, so here's our fish circle, here's our shark circle, and certainly you see anything that's in the shark circle has to be a fish. So if all sharks are fish, and if all fish have scales, so that would be the outer circle here, then certainly all sharks have to have scales. Okay, so that's a true statement. 34 is a nice picture to be drawn. If you have a isosceles triangle and you have these two base angles down here, base angles, they're the same, and the vertex angle up at the top, and you bisect it, so cut that into two equal parts. That will force this to be a right angle, and sure enough, you will have two congruent right triangles. Volume of a prism is given by 1/3. That's false. The problem, if it were pyramid, then it would be true, but because it says prism, no point at the top, you don't use 1/3, so that's out. Okay, so there's the first 6. Let's do the next 6. 36, 37, 38, 39, 40, 41, 42. I guess we have 7 of them here. Most of these are true. In fact, they're all true, except for 38. So these first couple and the remaining are all true. 38 is false. Which ones are interesting here? It says algebra. Let's do a little bit of algebra. For 36, it talks about the area of a circle. We know the area is, by definition, pi r squared. This problem says the area could be 5 pi. Let's see. Could these, in fact, be the same? Could 5 pi be the same as pi r squared? 5 pi equals pi r squared. Divide both sides by pi, so that goes out. And now we have 5 as r squared, so r would be the square root of 5. That's a true statement. There's your circle. Here's the radius, and if that were the square root of 5, then the area would be 5 pi. True statement. 37, the legs of a right triangle. Right triangles are important. Remember, good old Pythagorean theorem. So could the legs be 4 and 5? And the answer is yes. This would have to be the square root of 41, right? Square root of 16 plus 25, square root of 41. 38, the sides of a triangle could be 5, 12, and 18. That's a false statement. This is the triangle inequality theorem at work. I want to draw a little map here. Let's suppose we had two towns and they were 18 miles across. That's one of the sides of the triangle. And now we have these other two sides, and they say they could be 5 and 12. Now, there's obviously something wrong with this picture. If it's 18 miles going in a straight line, it can't possibly be 17 miles taking a detour. If you go from here to here, these two have got to add up to be more than 18. So possible triangle, no, absolutely false. 39, sides of a right triangle could be 5, 12, 13. That's a true statement. You should know your Pythagorean triples. 3, 4, 5, 5, 12, 13. And of course, there's an infinite number of these, but these are the ones that you encounter most frequently. If you're unsure, take 5 squared and add 12 squared to it and see whether or not that equals 13 squared. There's your question mark. 25 plus 144. This is 169. And sure enough, 169 equals 169. These are the sides of a right triangle. True. Number 40. The area of a circle with a diameter of 20 centimeters is 100 pi square centimeters. Little picture. Diameter is 20 centimeters, which means the radius, which is the part that we really need, the radius would be 10 centimeters. And we know the area is pi r squared. So the area would be pi times 10 centimeters squared. 10 times 10 is 100. And so the area works out to be 100 pi, and centimeters times centimeters is centimeters squared. True statement for number 40. 41, the perimeter of a regular octagon 8 times the length of its side. Absolutely. Regular means all the sides and all the angles are the same. So think stop sign. Try to draw a regular octagon here. There. And if we just call this S, and all of these are the same, because it's a regular octagon, the perimeter would be 8 S. That's a true statement. If a 30, 60, 90 triangle has a hypotenuse of 10, then one of the legs must be 5. It's a true statement. The way I like to think about 30, 60, 90 triangles is imagine a equilateral triangle for starters. So here we have 3 60-degree angles. Cut it in half. So now we have our 90 degrees. This is still 60, and because we bisected the top, that's 30 degrees. Okay, so the question now is, if 30, 60, 90 has a hypotenuse of 10, so if this is equal to 10, must one of the legs be 5? And the answer is absolutely. Notice that in the original triangle, 10, 10, 10, but we bisected this piece, so that has to be 5. So yeah, you should know the relationships in the sides of 30, 60, 90 triangles. Again, think about the equilateral triangle cut in half, and you should be okay. 10, 5, and then this one is always 5 square root of 3. It's always whatever this number is times the square root of 3. That's a true statement. Okay, next batch. Hope I'm not going too fast. 43, 44, 45, 46, 47, 48, 49, and 50. We have 2 false statements here. 43 is false and 48 is false, and all the others are true. So let's see what's most important here. The first 3 all deal with parallelograms. Diagonals must be equal. No, a little sketch would show you that's not true. There's a parallelogram, and this length is nowhere near that length. That's false. 44, they might be equal. Well, if we straighten that parallelogram up so it was a rectangle, then these two diagonals would be true, would be equal, so that's true. 45, they always bisect each other. That's one of the theorems on parallelograms. Make sure you look through all of those. That is true. Consecutive angles of a parallelogram could be equal. So let's see, here's our parallelogram. This and this are called opposite. This and this would be called consecutive. Well, in this picture, they're not equal. This one's acute, and this one's obtuse. But the question is, obtuse, could they be equal? Well, if we had our little parallelogram and sort of straightened it up a bit so that it turned into a rectangle, now you have two consecutive angles that are equal, so that is true. 47, the opposite angles of an isosceles trapezoid must be unequal. That sounds like a lot of stuff going on. Certainly I would draw a sketch. So we have our isosceles trapezoid. Let's think what isosceles means. Two sides are the same. Trapezoid, one pair of parallel sides. And now we're talking about the opposite sides, opposite angles of an isosceles trapezoid must be unequal. So this one and this one cannot be the same. That's the question. Now we do know, or I would hope you know, that the base angles do have to be equal. So these two are the same. And in point of fact, these are also base angles up here, even though they're sort of on the top. Those two have got to be the same. So do they have to be unequal? Well, again, if we tried to force them to be equal, what happens? Let's see. If we force these two to be the same, these two are the same, and then these two are the same. Now we're back to a rectangle, and we don't have a trapezoid anymore. We actually have a parallelogram. Trapezoids can only have one pair of parallel sides, not two. That's a tricky question. I'm not sure that would be a good exam question, frankly. Okay, 48. Both pairs of opposite sides of a trapezoid must be unequal. Well, we can look at this isosceles trapezoid right here. Certainly the bases are unequal, right? We have a long one and a short one. So there's one pair of unequal sides, but these are not unequal. These are, in fact, equal because I had an isosceles trapezoid. So 48 is false. A square is both a rectangle and a rhombus. That's true. You should look at the definition of both. And every rectangle is an equiangular, there's that word again, equiangular parallelogram, and that is true. Okay, so let's go fairly quickly. And the last batch on this page all has to do with circles. So let's throw the answers up first. 51, 52, 53, 54, 55, 56, 57, 58, and 59. Three of these are false. So 58 and 57 are false, and so is 55. The remaining questions are true. All of these have something to do with circles and cyclic polygons. So a circle can be circumscribed about any triangle. Yes, that's one of the constructions that you should know. Any triangle, there is one circle that goes through all three vertices. That's an ugly looking circle. A circle can be inscribed in any triangle. Yes, there is. There's one circle that fits inside every triangle, the incircle and the circumcircle. See, a non-regular pentagon can be inscribed in a circle. That's true. Think of a circle, and then a non-regular just means any pentagon that has 5 sides. So 1, 2, 3, 4, 5. Not regular. Obviously, this side is way longer than that one, but it is inscribed in a circle. That's a true statement. 55 is false. Every parallelogram is cyclic. Cyclic means you can put the vertices on a circle. And so let's see. Every parallelogram. Suppose I had a parallelogram that had way long sides like this. Is there a circle that fits through that? That's the question. First of all, that's not a parallelogram, Joe. Let's back that up a little bit. We want a parallelogram. So let's see. So here's a parallelogram. Is there a circle that fits through those 4 vertices? And the answer would be no. One of the criteria for a cyclic polygon is that the opposite angles have to be supplemented. So if this and this add up to 180, and if this and this add up to 180, then we'd be okay. but obviously we have a couple of acute angles here. They cannot be supplementary. And we have a couple of obtuse angles here and here, and they can't be supplementary either. So no, that's a false statement. A little bit tricky one there. Let's see. Every rectangle is cyclic. Yes, again, the definition of cyclic, you can put the vertices on a circle, and the criteria is if opposite angles are supplementary, these two add up to 180, and these two add up to 180. So yeah, we're good there. No problem. That's a true statement. Every isosceles trapezoid is cyclic. That's the one I was thinking of earlier. That's false. You could just draw an isosceles trapezoid, and you'll see, let's see, isosceles trapezoid. So we have, ooh, that may actually be true. We may have to go back and change. 57, that's a true statement. So sad. Let's talk about it. Isosceles trapezoid, what do we know? We know sides are the same, and these two sides are parallel. Okay, so, and we know base angles are the same. So these two are the same, and these two are the same. So we know that from our isosceles trapezoid. Now, is this cyclic? Well, let's look at opposite angles. Now, that's not cyclic. That is false. I was right the first time. I'm not sure what I was thinking there. Let's see. We know these two angles here are supplementary. Right? These are supplementary because they're same side interior angles. There's two parallel lines cut by transversal, and same side interiors have to be supplementary. But certainly the opposite angles are not supplementary. There's two obtuse angles. There is no circle that would go through those four vertices. So if you try to draw a circle, you would not be successful there. That's a false statement. 58. The ratio of the circumference to the radius of a circle is pi. We need a ratio. Let's see, the circumference ratio is 2 pi r, that's circumference, and the radius is just r. So this is the ratio of the circumference to the radius. Well, the r's cancel. That works out to be 2 pi, not 1 pi. So that's a false statement. 59. The perpendicular bisectors of the chord of the circle in the plane of the circle are concurrent. Wow, that sounds like a lot going on. So here's our circle. We have a chord, and we have a perpendicular bisector. So this is the perpendicular bisector of that chord. Then we have another chord. It could be anywhere in the circle, and we have the perpendicular bisector of that. And so the question is, are these two intersecting? Well, obviously they intersect. If we throw in a third chord, will it also be concurrent at that location? And the answer is yes. So the perpendicular bisectors always meet at the center of the circle. So that is a true statement, concurrent at the center. Interesting question. Okay, let me stop this one here. And okay, a little bit less time, still rambling on, sorry about that. 18.